So this is going to be a really quick video, just looking at one small part of the specification from the Mech Minor syllabus related to the moments related to equilibrium. So in this force diagram I've got here, I'm going to say I've got some uniform lamina with three forces acting on it. We've got a weight downwards acting in the middle. We've got a reaction at the top left corner, which could be from a hinge or something, or from a wall. And then we've got some pushing force in the top right corner. Now, I'm going to claim that we know for certain this can't be an equilibrium here, regardless of the values of P, R, and W, at least if my diagram's anything like accurate. Now, the reason for that is that if something's equilibrium, then yes, we know that the total moment is zero. But if something's in equilibrium, the total moment's zero regardless of the point we take moments about. And if we pick a point to take moments about that the lines of action of two of the forces goes through, then we'll see what happens. So let's just consider the top right point here, A. Now, obviously, the force P goes through the point A, and hopefully, clearly, the line of action, the force R, goes through the point A. So if we're to do moments about A, P is going to cause zero moment, R is going to cause zero moment, but W will cause an anti-clockwise moment of W times whatever that distance of the line of action from W to A is. So it's definitely going to be a non-zero moment. We're definitely not in equilibrium. Now we can expand the idea as if we have two forces meeting at a point and the third force doesn't go through that point, we're always going to be able to do moments by that point and say we've got a non-zero total moment. So that leads us to the theorem now we're looking at today, which here's one I prepared earlier. If three forces are acting on an object, this only works if there's three forces, not if there's more. But if three forces are acting on an object and they're not all parallel to each other, then their lines of action must meet at a single point. The reason for the not being all parallel to each other is because then you don't even have a point that two of the forces meet at. So this is sometimes known as the three-force theorem. I've included the bit from the specification here as well, just so you can see exactly what it says. And it's this sentence down here that's the important bit. Three forces in equilibrium must be concurrent. By that it means their lines of action go through a single point, or parallel. Now, it doesn't go both ways. Just because three forces are concurrent doesn't guarantee they're in equilibrium. Obviously, in this example, that would depend on the values of R, P, and W still, even if they were going through the same point. But if they don't all go through the same point, we know they can't be in equilibrium. So I want to look at one example using this now. So the example I'm going to look at here is I've got some weird shape here, just kind of a blob. I'm going to tell you the center of mass of this blob is at 0, 0, so I'm just calling the origin that center of mass of the blob. And I'm telling you it's held in equilibrium by two strings. One of them attached at negative 1, 4, with an angle of 45 degrees to the horizontal, and one attached at 2, 7, with an angle of theta to the horizontal. I'm not going to tell you what those forces are. What I want to find is we want to find out the value of theta, so this is necessary. Now, you could try doing this by labeling the tension in both strings, T1 and T2, and resolving horizontally and vertically and doing moments at a point. It gets really pretty horrible. If you're not sure, try it out and see what happens, but you'll see it really doesn't get very nice because you're going to have a T2 cos theta, a T2 sin theta involved. Things get really messy pretty quickly. So instead, I want us to try and make use of this theorem that we've got. We're told there's three forces. They're definitely not all parallel, so they must be going through a single point. So let's try and investigate what that point is here. So if we continue the lines of action here, so I'm going to look at W and this one here, they're going to meet at some point here, which I'm just circled around here. If we can work out the coordinates on the point, we're going to be good. Now, W is clearly a vertical force. So immediately, I know the x-coordinate of this point is 0 because it's just directly above my center of mass, which also had x-coordinate of 0. The y-coordinate, a little bit messier. We need to think about this 45-degree angle, there's a reason I've given you 45 degrees. It'll make life a bit nice. But if I make a little triangle around here, I know that I'm going across by 1 because I'm going from -1 to 0. And if this is 45 degrees, then just by very simple trigonometry, tan 45 is 1. So this, I'm also going down by 1, which tells us I've gone down by 1 from a y coordinate of 4. So this coordinate here is going to be 0, 3. Now, that's really useful for us because that's telling us that the line of action of our third force, this 1 at T7, must also go through that point there. Now, it doesn't look like it because I've drawn it quite badly, but that line of action must go through there. So actually, I'm going to slightly redraw that to become this line here instead. So that purple line's taken over because that's going to be a bit more accurate. Now, if I draw in this purple triangle here, hopefully you can agree that this angle is also going to be theta by corresponding angles. We've got the horizontal lines being parallel lines there. So we're trying to find theta, and well, we know just two lines here. We've got a right angle triangle. The change in x from 0, 3 to 2, 7 is 2. The change in y is 4. So tan theta is going to be 4 over 2, and now we can just do theta is arctan of 2, which gives us 63.4 degrees. This isn't a theorem that comes up loads, but if you get a question with an unknown angle like this, and you've got three forces, sometimes it can make your life an awful lot easier than any other options you've got available to you. Thank you very much.